Okay, going to go through the final lecture on vector algebra, lecture 8. Let's see what the content. So we're going to look at vector calculus. We're not going to go through the detail of derivations of vector calculus, but we're going to try and show you how it, what we've seen in terms of vectors fits in with calculus, particularly differentiation, because this becomes extremely useful when you want to look at some the generalization of three-dimensional mechanics, for example, fluid dynamics. In 3 dimensions it becomes essential to do things in vectors, else it gets far too complicated. And then we'll briefly summarize what we've done in this course. So, vector calculus. Let's consider a vector A with a single variable u. For each value of u, we associate a vector A, and we've written down AU, so we've got this vector for each one. And in Cartesian coordinates, we might write this down as the components of ijk. So AX, U, AY, U, AZ, U. So those are the three factors of U for the vector. So scalar components of U are the AX, AY, AZ. A derivative of the vector A with respect to U would be simply the same as what a derivative would be for any scalars that you're normally used to working with. So dA du is the limit as u goes to 0 of A plus delta U minus AU. So a small step in A divided by a small step in U, with the small step going towards 0. So that's the definition. So how would we write it down for a vector? Well, we'd just write it simply like this. We do the operation on each of the 3 scalar components. So pretty straightforward, really. Let's just think about this in terms of velocity and acceleration in mechanics. If we have a position vector, we look at that change in position vector with time, we get a velocity, we change it, we differentiate that velocity, we get acceleration. You know that. Let's see how we do it for vectors. So a position vector R, and we're going to write it as x, y, z, we know that, differentiated with respect to time. So dx dt, dy dt, dz dt. Those are that is now given as our velocity vector. We differentiate that velocity vector. We've got to be dv dt, dv t, dvy, dvz, dt. So we have acceleration. Of course, acceleration is the second derivative of the xyz of r. So d2x t dt squared plus d2y t dt squared plus d2z dt squared in vector format. Okay, so not too difficult, I think, not too much a step from what you already know of differentiation. Let's have a look at a particular example. It's usually easier to look at things as an example, but really it shows you how we can do differentiation and then apply the vector rules that we've seen previously. So we're going to look at this position vector in terms of t. So it's showing the position of a point, how it changes with time. Take t to be time. Find the speed at t equals 1. So we find the speed at t equals 1. So we need to differentiate this position vector and to get v. and we need to substitute t into that. But we need to find the component of the acceleration along the direction of this vector. So that's where we're going to do our dot or scalar product and find the position of, the component of acceleration along this vector. So we're going to see two derivatives to get the velocity or the speed and the acceleration. So our vector, we differentiate. It simply comes to differentiating each of the terms. So 2t squared goes to 4t, 3t minus 2 goes to 3, 3t squared minus 1 goes to 6t. So we'll differentiate again. 4t goes to 4, 3 goes to 0, so that term's going to be crossed out. 6t goes to 6. So we get the speed. Remember, it asks for speed, so magnitude of the velocity vector, which is just the square root of the squares. It's got t in that expression, so we wanted it t equals 1, so we substitute t equals 1. And the speed at time equals 1 is root 61. Whatever the units are, we're not told the units, but root 61. The acceleration will be acceleration vector times by a unit vector in the direction that we were looking for. So our direction is I plus 2j plus k. The unit vector will be that vector divided by its magnitude, so 1 squared plus 2 squared plus 1 squared square root, which is root 6. So we dot those two vectors, divide by root 6, and this number, 5 root 6 over 3, is the component of the acceleration in the direction of 2j k at any time, because there's no time expression in this. Okay, so a simple example, which I hope was in the context you'll understand, of vector calculus in terms of, or calculus in terms of vectors. Let's have a look at another example, and this is circular motion. Why circular motion is quite interesting, and how we will look at it in terms of vectors. We've got velocity going around the circle. We see it's changing all the time, and acceleration is changing, but it's at right angles to the velocity vector, and we know that we can get right angles from vectors by looking at the dot product, where cos 90 is minus 1 and 0 would be cos 0 is 1. Okay, so we have velocity squared equals a constant. We have dv dotted with t is equal to 0. What's that mean? So dv squared v dotted with is equal to 0. So either v is a 0 or the cos of the angle is equal to 0. So the cos of the angle is 1. We've differentiated v. We can expand that dot product, because we can expand brackets, and we get v dv dt, or dv dt dot with v. So we need to do two dots here, is equal to 0. Rearranged, that equals to 0, so that we know that v is right angles to dv dt, which is acceleration, which demonstrates this. Product rule is expanded for vectors like this. For scalars, a scalar times a vector, we just do the product rule on those as we would normally. For the dot product, similarly as we would normally with a dot product, and for the cross product, similarly as we would normally do in the cross product that you're familiar with. So product rule that you're familiar with. Scalar and vector fields. Well, what are scalar and vector fields? So this is what we mean by scalar and vector fields. This is a scalar showing, for example, pressure. Pressure is a scalar field. We can represent that with a vector, and the derivative. We look at the derivative, which shows the angles. We differentiate a vector field. We may have velocities and accelerations if we have to. So those are two quick, simple examples, hopefully familiar, where you can see how we get a vector field or a scalar field in practice. We have sort of notation that is to enable writing down of equations in vector form simply, and we have this so-called div operator or grad operator, which looks like this. So the grad of phi would be written grad phi is equal to this. So writing grad phi is a short way of writing this large vector notation out. So it simplifies things. And phi in a particular direction would be grad phi dot a, where a is this unit vector in the direction you're interested in. So simple notation there just to be aware of, and summarise this simple notation and the names for it. The gradient can be sometimes written grad of f, and that will be written as grad. For example, measures the rate and change of a scalar field and direction of a scalar field. We see that in maps and scalar field and scalar fields with vector fields. Curl is the cross product, so it's div operator with the vector is called curl, and it's looking about the rotation of a point around the field. And the divergence operator is sometimes written div f, or this div operator dotted with the vector. Measures the scale of a source or sink in a given point in a vector field. So these are common things just to be aware of as far as this course is concerned. Now this vector algebra is not going to be, this vector calculus is not going to be assessed as part of your exam for this course. Just these are about being aware. Let's have a look at a summary for this module. Now we frequently use vector notation when we're looking at forces, position, vector, acceleration, and doing things like calculating moments and distances. Vectors are quantities that completely defined by a magnitude, or sometimes with units, and a direction. Not necessarily a specific point where they're applying, unless we're applying them to a point position vector, so they're relative to another point. Vector algebra, some topics we've looked at: vector modulus, unit vector. And all of these are key actually. Multiplication of a vector by a scalar, vector addition, parallelogram rule, triangle rule, or in vector form, just add the components. Scalar multiplication of two vectors, the dot product. Vector product or vector multiplication, the cross product. Practice doing that with your determinant expansion. Vector equation of a line, vector equation of a plane. Modulus of a vector, simple. We apply Pythagoras to the 3 points, we square each, sum them and take the square root. Unit vector is the vector divided by its magnitude. So if we worked out the unit vector of the magnitude of this unit vector, it will be 1. It's always going to be 1. But it's a vector in the direction of the original vector. Multiplication by scalars, we just multiply each of the components by the value. Vector addition, we have the parallelogram rule. How we can form that parallelogram rule is by moving, because the definition of vectors means they're not defined by a point, we can move them. So B here has moved to B here, forms a triangle or forms a parallelogram. We can do in component form, we can do the cosine rule to work out these different lengths and angles, but because we can move them, we can do addition geometrically. So we might use the cosine and the sine rule to solve these if we're going to do geometric addition. So be aware of doing the cosine and sine rule for the triangle that's formed and understand how to do that. The dot product, scalar product, is defined as this, where theta is the angle between the two vectors, and it's in the first quadrant, first 180 degrees. Component form, it's A dot B is multiply each component and sum them. Two important things about the scalar product, it's a product of two vectors. So it's called scalar product, but it's not a product of scalars, it's a product of vectors. And the result is a scalar. That's why it's called a scalar product. So it's a vector operation to produce a scalar, a number. Typical application of the scalar product or the dot product is that if is looking at the component of a vector in a particular direction, and this turns out we can work out if what the vector is a force and a particular direction is the represents a distance, and we can work out the work done along that distance or line vector r by a force, and it's just F dot r will give us the work done. Let's have a look at a simple example. This example is one you've seen before, but have a look at it again. Just do it now in your own time. Be assured you can do these simple examples in the next few slides. Find the work done by the force F moving a point from point A to B, which have position vectors, these two. So we need to take those 2 points, work out a vector between A and B. So A to B is B minus A, 5, 4, 1 in this case. Work done is F times R, which is the AB in this case. So F dotted with R, so we need to do the dot product, which turns out to be 2 times 5 plus 1 times 4 plus 3 times 1 adds up to 17. So that's the work done. The cross product, remember the cross product is written like this: A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between the two vectors times a unit normal. So it's a vector normal, and it's a right-handed rule. So if your first finger's X, second finger's Y, the thumb is Z. Or you grab the axis, you go around in the XY direction, and your thumb is Z. We can do this calculation if we've got two vectors in a plane, and we often get two vectors in a plane by joining 3 points together to get two vectors. We can do this cross product by expanding a determinant. in this way. If you're not used to determinants, get used to doing this expansion. You will use determinants again when you see matrix algebra later in this course. Vector multiplication, anti-commutative. So we get with the cross product, A cross B is equal to minus B cross A, because we get our thumb pointing in the opposite direction if we move from Y to X with our fingers. It's non-associative, so we can't expand brackets. Distributive for scalar, highlighted there that the vector product produces a vector, so we can do vector times vector times vector. Applications for the cross product, we can find the perpendicular distance from point O to R. We can calculate the moment without calculating that perpendicular distance, because it becomes part of the calculation. So if we just need a point on the line of action of the force, we can find the moment about the origin of that point. And this is a typical calculation, calculating moments about points. So the moment, if R is a position vector, F on the line of action of the force, and F is the force, the cross product gives us the moment about the point of origin of R. So let's do an example problem of that. The force F is 13 newtons, acts at a point there, so there's our point, and in the direction of the vector 0, 12, 5. So first thing we need to do is convert this 13 and the vector into a vector format. So find the moment of the force about point P, 1, 2, 1, 2, 1. So we're going to have to find the relative position of Q and P. The unit vector in the direction of the force is just the force divided by the magnitude, the vector divided by the magnitude. Thus the force vector is that unit vector times by the magnitude of the force, which was 13 conveniently, so this 13 crosses out. So we've got a force vector, position vector of P relative to Q. We subtract Q from P and we get 1, 0, 1. So the moment of the force about P is the cross product of PQ and F, which expanded, learn this expansion, is 5 minus 5, 12, and we can work out a magnitude of that by squaring each, summing them, and taking the square root. Vector equation of a line. We define 2 points on the line and a vector joining those 2 points. So in fact, we don't need those 2 points. We need the vector in the line, but it's convenient to have 2 points. We do need one single point, so we normally take point A and say that A plus a multiple of a vector in the line defines any point, and we usually say P defined by R is the vector equation of a line. Each of these components are x, y, z for R, A1, A2, A3, and B1, B2 is for B, and we can expand that and equate them to T. This is the usual convenient form. It's a slightly strange form, but this is the way we normally represent the Cartesian form of an equation of a line. Simple example. We need a vector in the line, so we've got a line joining 2 points, A and B. Vector in the line is B minus A. So 1 minus 3, 5 minus 2, 3 minus 1. equation of the line is a plus tb minus a, and a 3, 2 minus 1, 3, 2, 1. So equation of a line joining 2 points. That line in fact goes through the 2 points, goes on through infinity. Vector equation of a plane. We have a vector in the plane and we have a normal. We actually just need a point in the plane. So r minus a, which is a point in the plane, times by the normal is equal to 0. So the vector in the plane is, the vector equation of the plane is a dot n. So the cross product, sorry, the dot product is equal to a dot, r dot n is equal to a dot n, or r dot n equals to p, because this a n gives you a constant. So r dot n is equal to some constant. We can substitute x, y, z for r, and n1, n2, n3 for n, and this gives us the Cartesian form of the equation of a plane. Let's look at a quick example. You've seen similar example before. I'll go through this now and just make sure you can do it. 3 points in space. We can draw a plane through 3 points in space. We need 2 vectors, so let's get 2 vectors. Now they can be any difference or any of these two. We've chosen BA, CA, gives us two vectors. We cross the product these to get a normal. So we go to normal, 3 minus 5, 1, 3 minus 5, 1, r dot n, r dot this normal is equal to a point in the plane, and the first one could have been 1, 2, 3, it could have been any of the other points, dotted with n to give us this a constant. This is minus 4 in this case. So the equation of this plane is r dot 3 minus 5, 1 minus 4. Final things. Just remember, in engineering analysis involves quantities that have magnitude and direction. We use these all the time. Force, position, velocity, acceleration, super common. In fact, that's probably all we use, and we keep going on. We'll look at energy, which is more scalar-like. And we usually do this in 2 dimensions, and it's quite straightforward in 2 dimensions. But as soon as we get into 3 dimensions, it gets much more difficult, and a vector approach is usually the most convenient. So when we go further into the course, you start doing 3-dimensional simulations of, say, fluid dynamics or mechanics of bending of buildings, and you're looking at stress and angles and moments. You need to be doing 3-dimensional calculations, and you need to do those in vectors. And all computers, when they're doing an analysis in 3 dimensions, they'll do it all in vector arithmetic. So useful to understand vector arithmetic. Thank you.